Yeah, welcome back to the second part, main challenges, potential pathways and conclusions. And it's now my pleasure to open this second block of the afternoon with the announcement of the next presentation is delivered by Georg Brasseur, who is the former president of the Division for Mathematics and Natural Sciences at the Academy. Georg is emeritus professor at the Institute of Electrical Measurement and Sensor Systems at the Technical University of Graz and member of the Commission for Interdisciplinary Ecological Studies. As mentioned before, it was him who laid the foundation for the joint working group on energy transition by delivering a much referred talk that put the numbers on the tables. Finally, after many years of review, as you ensured us, one can refer to it as the inconvenient truth, and questioned if energy transition is actually achievable in Europe. He will now focus on a specific but crucial aspect, and Lucy has actually touched upon it: energy storage across temporal scales. Georg, the floor is yours.
Thank you very much for the kind introduction. Yes, when talking about energy, I always think about nature. For nature, it's very important for all the living beings to have energy available. And therefore, in my first slide, I say, what can humans, in terms of energy, learn from evolution? And maybe we can find interesting answers. Life exists since 3.5 billion years. Long time. And the hostile environment causes an evolutionary adaptation to the environmental conditions in all living beings by a random mutation. So this survival of the fittest method we also use in engineering. It's marvelous. Unfortunately, it takes long times, much more time than we as humans have. But the outcome of that are, for instance, mitochondrium. These power plants of living organisms, they were formed just by chance, and they are very powerful and very successful. Otherwise, they wouldn't exist for such a long time. And they will have two substances within. It's more or less a battery, a biological battery. The ADP, the adenosine diphosphate, and the adenosine triphosphate. So that you can charge it and you can discharge it. And discharge means the cells get some energy in terms of heat, and you need something to recharge it. And the recharging happens when you have anaerobic life, so cyanobacteria. You use nitrogen to give hydrogen a higher... So to give hydrogen a higher volumetric energy density, nature found it's a good idea to couple hydrogen to nitrogen, and you can use that to charge, let's say, this ADP to ATP. And in an aerobic life, you're using glucose to power this circle. So these storable energy sources are essential for the survival of all living creatures. And humans should learn from evolution. Hydrogen as an energy carrier is essential, but it's only successful in evolutionary terms if hydrogen is atomically bounded to carbon or nitrogen. So that you have, on one hand, carbohydrates or alcohol or ammonia if you're taking nitrogen. So what would be the ideal transport and storage container for hydrogen? Pressure or cryogenic? The gravitational energy, the caloric value of hydrogen is enormous. It's 33.3 kilowatt hours per kilogram. But for a volatile gas, it's not very helpful because you need a container. So the volume energy density counts. And the volumetric caloric value in kilowatt hours per cubic meter measured of hydrogen is just 3 kilowatt hours per cubic meter. At ambient pressure, if you use 700 bar. That's the pressure you're using for hydrogen cars, for instance, for the tank. If you even cool it down to minus 253 degrees C, then it's quite big. But if you compare it to, let's say, what we learned from nature, if I bond it to carbon, for instance, we will get methane. And with methane at environmental pressure, we have, instead of 3 kilowatt hours per cubic meter, we have 9.9. So it's 3.3 fold more. So we have, and that's quite interesting, we're getting 3.3 more out. So you have a fat and thick atomic weight 12 carbon sitting in the center, but this carbon draws the 4 hydrogen atoms very close to the center. And so we can get a much higher volumetric energy density. And the same is if we look to at the typical pressures for methane is 200 bar and for hydrogen is 700 bar. We're still gaining 1.5. And if you cool it down to minus 162 degrees C, that's for methane. And for the hydrogen, it's minus 250 degrees. We still have a gain of 2.6. This means even if you use those two substances in the liquid form, we need 2.6 more storage room to transport. So in terms of storage, it makes very much sense to use these bondings. Another way, as I showed, nature also said nitrogen is a good means to increase the energy density. If we do that, we end up with ammonia, and this ammonia has 1.3 times more energy density during environmental pressure. And if you cool it down, and that's a huge benefit because you just need minus 33 degrees C for ammonia, and for hydrogen, minus 253. And most of all, nitrogen is not, let's say, it's not a greenhouse gas. So you can take the nitrogen from the atmosphere and can release it wherever you want, and you will not have an impact in terms of global warming. With carbon, it's completely different. So if you take the carbon, and nature has the carbon in the cycle, the trees collect the CO2 and store it and release it again. So it's a closed cycle. And the same we have to do as human beings. If you do that, keep it in a closed cycle. So that's the big challenge. But I'm pretty sure we'll handle this problem. So we can learn from nature. The ideal transport and storage container for hydrogen are chemical bonds, either carbohydro or, we have it here, then we have synthetic liquid or gaseous fuels. Or we bond it to nitrogen, then we have synthetic ammonia. So the energy of wind and solar is very, very poor compared to fossil fuels. And to give you a flavor of that, I have an example. We take a huge wind park. A huge wind park, we have it here, Arkona, it's in the Baltic Sea, it has about 40 square kilometers, and I take 2.6 the size of this wind park, then we end up with around 100 square kilometers. And these 100 square kilometers will then produce around 1 gigawatt. And this wind park has a utility rate of 44%, and this gives 3.9 terawatt hours. And then we convert, or we use this electric energy to produce, with power to X, liquid methane or diesel fuel. And the efficiencies are between 43 and 71%, depending on the type of substance and depending on the process we're using. And so we're ending up with 1.8 to 2.8 terawatt hours per year that is available. And then we need a transporting vessel. We need a tanker. And an LNG, liquid natural gas tanker, but it could be as well a liquid synthetic methane tanker. So it's the same vessel. And it contains 250,000 cubic meters, and with diesel it's 350,000 cubic meters. And now I have a question for you. How long do you estimate it will take to fill this ship? Usually such a ship is, let's say, loaded and unloaded within 12 hours or something like that when it's fixed to the pier. It takes 7 to 10 months for the liquid nitrogen and 1 to 1.5 years for the liquid fuel. It's a very long time. This means it is important to convert the green energy into a transportable form that you can carry and bring from A to B, as the energy density is quite high. Wind and solar have an energy density orders of magnitude lower than hydrocarbons, and the transport losses of hydrocarbons are almost negligible relative to the energy content. Such a ship needs lots of fuel, but it contains so much energy, the order of magnitude 3%, 4% of the load of the ship will be used to transport the fuel. And the best transport and storage option lies in chemical bonds, as I already said, either ammonia, then we do not have the problem with the nitrogen, or with hydrocarbon, then we must keep the carbon in a closed cycle. So if we analyze European primary energy demand, it was in 2019 17,100 terawatt hours. It is given here the breakdown: oil, gas, and solid fossil fuels. If we want to deliver that by means of wind turbines, we have to multiply the number of wind turbines by number of 36 compared to the 82,000 wind turbines we had in 2019. Of course, this is crazy, that's ridiculous. But just to give you a flavor, how much, let's say, green energy you need to compensate that. Of course, you can say, we will save energy. Saving energy is the most important issue for an energy transition. On the other hand, we are so far not so clever to do what nature is able to make out of green energy a transportable energy carrier, glucose. We cannot do that so far. So this means we have to convert 1 or 2 times. And the conversion, again, has losses. So we cannot say we save 90% of these 17,000 terawatt hours, because we also have conversion losses. We could do it with wind, not with wind, with photovoltaic as well. And that's even worse. With photovoltaic, we would need to increase the size, this area of 2,000 square kilometers, by a factor of 111. What is scary is not this number. What is scary is the extra load that would be introduced to the grid. 16,000 gigawatt. Forget it. It's more than 10 times of the total European power plant capacity. Forget it. The same is in Germany currently with more than 60 gigawatt of photovoltaics, but 98% are on the rooftops of private houses. So the utility company needn't take care of how to deliver these high power values to somewhere. So that's a big issue. Therefore, I'm very much in favor to collect the energy when we need it and make a much higher energy density out of that and deliver it. And then most of all, then it's a storable energy and we can release it when we need. And finally, the European Union sometimes do not have it really in their minds. 320 billion worth of energy products were imported. And as it said here, 85% of Europe's energy was imported, and 320 billion each year. So, and out of that, we get the clue, Europe is not and will not be energy autonomous in the future. This has a high impact, because then we say, we have to import a specific type of energy, 1 or 2 or 3 energy carriers. And a few other energy carriers we have to do on our own in Europe. And so we know out of sun and wind current, we just get electricity. And the bad news with electricity is electricity does not have energy. It just brings energy from one side to the other. And we should have a look to how much raw materials we need to build, for instance, these windmills. For the construction of these 3 million onshore wind turbines, at the time, 2019, the average power was 2.5 megawatt. We would need 3,000 million tons concrete. This is about 15% of the world production. This number is not very precise because it depends very much which type of windmill you will use. So it is varied, but you get an order of magnitude. And I just want to convey the orders of magnitude we need. Or 1,100 million tons of steel. This is 55% of the world production. Horrible. If we would have made a mistake by a factor of 5, it's too much because Europe is just 8 to 10% of the world. Primary aluminium. Aluminium is lovely if it's already there, because then you have it more or less in a cycle. You melt it and you produce something, you melt it again, but not if it's a primary aluminum. Then we need about 10%. When you look copper, it's worse. Copper is horrible. And that's just the quantity of copper you need for the windmill, not for the wires to connect the windmill to the grid. And if we are offshore, the 90% additional, just as a rule of thumb, are added for the wires from the windmill, a few miles out on the open sea, to bring the current into shore. So just from here, we say, can't do that. With polymers is also a problem. Polymers, we do not have so much on the world, and you need lots of carbon as a fibers for the blades of the windmills, and it did X-fold the world production, so it doesn't exist so far. So the construction of green infrastructure requires huge amounts of raw materials and releases large amounts of greenhouse gases. So the threatening thing is the big amount, not so much the CO2 emissions, they are also big, but the availability of those raw materials. And the yield of the harvesting plants must be high. So we do not need 3 million, perhaps just 1 million, then we save some energy, then just 500,000. And this means we need the best possible location. And these best possible locations are abroad, they're not in Europe. A few we will find, lovely, but not this big number. And save energy, of course, save energy. And how to make optimal use of the electricity generated in Europe. I remember, currently we just have 70% of the primary energy is electricity. In the future, it's only electricity. Of course, we have some nuclear power and we have some geothermal and so on, but the big mass comes from current now. Wind and solar energy provide electricity that must be consumed because we know already electricity has no energy. It just transports from wind power or electricity or solar power to via current to the households. And it is information and communication systems or the technology, households, lighting, railroads, electric motors, industry, and so on. A first lossy energy conversion process makes out of the current, makes green hydrogen. And the green hydrogen is very important for the industry. Industry needs it on one hand to get out the oxygen from raw materials. It could be steel, so you must get out oxygen. And there you need hydrogen. You can use. So far we're using carbon and produce CO2 out of that. In the future we'll produce water out of that by capturing with hydrogen the oxygen in the raw materials. So industry needs, and additional industry needs, high temperatures for the production processes. There are also, hydrogen is quite helpful. A second lossy energy conversion generates all those fuels I already mentioned. It's more or less a copy of what we have today in form of fossil fuels. So the minimum, also to minimize the number of energy conversions, minimizes the primary energy demand, minimizes the raw material requirements, and thus also greenhouse gases, of course, and minimums the capital investment cost and the operating cost. And this means the optimization problem can be solved on the sound basis of scientific facts and should be unaffected by logical or political opinions. You can just write down numbers. And out of that, you will figure out how much energy you have to import and which type of energy you have to import. The grid losses, and I will start with a funny example. I take, if there's no police around, I take a fast sports car and race from Vienna on the highway with 200 kph to Munich. These are 400 kilometers, it would take me 2 hours. I drive like hell, but this is quite, it's stressy. So you stop perhaps after half an hour for a stop. So you drive very fast, then you have a stop. You drive very fast for a stop. So if you do that, if you make 4 stops, half an hour, and drive also half an hour, then I have 2 hours drive time. I will make it within 2 hours the drive, but 2 hours rest time, so it takes me 4 hours. I could as well drive with 100 kph the whole time, and I will reach Munich in 4 hours as well. But what I will find out, the fuel consumption was horrible when I was sitting at 200 kph. Why? Because the air drag goes up with speed squared. And that's the same with the power lines. And that's a drawing of a root mean square current, the orange line. So you transfer energy from A to B permanently, like with thermal power plants. And in the other case, like racing before, I take a high current, double value, and then nothing, because there's no wind. Here, I have double current. This means 4 times the losses. And as I said before, the losses go up squared in terms of current. It's here. Losses go up squared, and the resistance of the net is linear in terms of losses. But therefore, we have here 4 times losses, and if we go down to a duty cycle, and that's just the on and off time, there's a factor of 3. This means 9 times more losses. Just what I want to show. A new grid, a grid that's powered with volatile energy, with non-dispatchable energy, cannot transfer the energy we're used today. Because today we're using this orange line. The orange line where we transport as long as we can energy. But in the future, we have to take the energy when it's there, high power, and the losses will be higher. So the grid is not able to deliver the same quantities as we had before. So for non-dispatchable energy to consumer-generated energy systems, we should do something for that, because we're not used to a volatile energy, to a non-dispatchable energy. And as long as other industrialized nations, and I think that's a very important issue, use predominantly fossil fuels, Europe will lose global competitiveness by switching predominantly non-dispatchable energy system, because this crude oil and the gas will go to other nations. They can produce the goods very cheap with fossil fuels, and we have this fancy new green energy, and that's expensive. So industry will go away, because industry cannot afford to produce their products with expensive energy. And that's a big issue today. So this can only be tackled, Hans-Werner Sinn already mentioned, he calls it climate club. If all the industrialized nations join and say, we do specific things together, that's the only way that the fossil fuels will be reduced. And the first time since 50 years they were reduced when Corona came up, because all nations went down with industry. So the only chance is if they unify and say, okay, we do something together. Elsewise, Europe will be the big winner in terms of green energy and the big loser in terms of industry is gone. We have no labor anymore. So this is very sensitive. So what we need, additional power plants to bridge the energy gaps of non-dispatchable energy. So we need a parallel system. That's quite expensive. More or less, these system is there and sits and waits till there is no sun and no wind, and has to kick in and control that demand and supply is equal. So this causes additional and considerable personnel, maintenance, and operating costs. The components for the power gaps, up to, because you must control it, up to almost grid capacity must be there in this shadow system. So the whole grid power, because if we have those cold, dark doldrums, no wind, no sun, we need the full power from other equipment. But this other equipment exists. We have that today, predominantly in caloric power plants operated on coal and gas. Coal is a definite no-no, but you can also operate those power plants on gas. So they should be, of course, in the future, powered by green storable energy, or the fossil CO2 emissions are compensated via carbon capture and sequestration, for instance, into basaltic rock or oil field. Norway offered to the European Union. They take all the CO2 released from energy production and store it in the oil fields. It's an option. A second thing that will happen, Lucy already mentioned in her talk, that from time to time we have to curtail our wind or solar production. We will not curtail it. We will use it and power, recharge short and long-term storages. Batteries and pumped hydro can only store small amount of energy. There we're discussing gigawatt hours, but not terawatt hours. And we're discussing before 17,000 terawatt hours. So we need storages in the terawatt hour range for seasonal storage, not for the minutes and hours and daily, perhaps weekly. Synthesis gases and liquid fuels are ideal for seasonal energy storages. Synthetic methane can use existing infrastructure like storage, distribution, and power plants capacity. So we do not have to invest again CO2 by using materials to build it up. Therefore, I'm not a big favor. It's not a big. We read so much in the newspapers now. We made a new hydrogen grid in Europe. We have 500,000 kilometers of pipes for hydrogen, not hydrogen, for methane within Europe. So we should use that. It's also a matter of saving. Saving energy means use goods longer. Do not buy new ones. Use it longer. It's exactly the opposite what we learned 20 years ago, consume goods. It helps the industry. And finally, ammonia is a readily transportable, storable base chemical, and can additionally be used as energy vector. And hydrogen is an important product agent for the industry, but not a significant intercontinental energy vector. It does not exist so far, because we do not have ships and pipelines. And it would take very long to bring that up. And finally, we have more or less a new grid that is now for hydrogen, not for methane. It's much smarter if we find ways to keep the carbon for the methane in a closed circle, like nature is doing. And just at the end, so that you again get the flavor for Austria, the gas and electricity consumption in Austria, and you see the fluctuation in the electricity consumption over the year. It's 0.15 to 0.2 terawatt hours, yeah. So 100 gigawatt hours fluctuations. And in the gas, it's much more. It goes from 0.1 to 0.5 terawatt hours. It's about 3 times more. So we have much more, and households play an important role there. And here it's the comparison of those storages. The storages in Austria is about 60 terawatt hours and about 1.7 terawatt hours for pumped hydro. And these are the lines coming from E-Control, so that's a credible institution. And that's the maximum capacity for the pumped storage over the year, and that's for the natural gas. So in a summary, I can say green hydrogen is an excellent reduction process agent for many industries, but not an energy carrier because of the poor volumetric energy density and lack of large-scale infrastructure. We have nothing for that. Yes, humans should learn from nature that hydrogen, atomically bonded to carbon or nitrogen, is an ideal storage energy carrier. Europe is not and will not be energy autonomous. Humans are, let's say, it's like a big inertia. We cannot change the direction immediately. So it will take very long till human will adapt. And we must live with that. And this means Europe will not be energy autonomous in the next few 10 years. And neither electricity nor hydrogen can be transported intercontinental. Therefore, Europe must produce electricity and hydrogen from the own electricity, wind and sun, on large scale in Europe. And the good news is the electrolyzers you can build in a way that you can use very powerful wind current or not so powerful. They can adapt to different power levels, and the outcome is already a storable substance, hydrogen. You can store it. Of course, our storages will just take 30% of what you can store with methane, but you can use them. And additional power plants serve to bridge the energy gaps and to transform the European supply-driven, non-dispatchable energy system into a consumer-driven one. That's very important. And a temporary oversupply of wind and solar power plant charges short-term and long-term storage facilities. And finally, highly efficient battery and pumped storage power plants can buffer the fluctuation electricity for only a few days, predominantly morning till evening, sometimes shifting 2 or 3 days. Week is almost too much. And the energy demand for the seasonal shift, it must come out from gases and liquid green energy sources. And these gases and liquid energy sources, we must predominantly import from countries where you have a much higher harvest of wind and solar energy to save natural resources, to save raw materials. So thank you for your attention, and I'm happy to answer your questions.
Thank you, Georg, and in particular for bringing the numbers into perspective. I think this is important from times. And also an important aspect is, of course, how much additional energy and resources are used for the energy transition and how much additional sequestration, carbon is released to the atmosphere. Mm-hmm. So I will open up the floor for questions, but please keep it brief.
This was very impressive, but you did not mention among the materials which are necessary, the rare earths, which are necessary for wind power plants, photovoltaic, and batteries. How do you foresee the amount of rare earths and rare metals which are necessary and their availability, the political risks involved, etc.?
Well, I think I mentioned already, batteries are very nice for our mobiles and for our computers, but batteries, the current existing batteries, lithium-ion batteries, they are not made to, let's say, to store huge amounts of energy. And huge amount of energy start in the terawatt-hour range or a few hundred gigawatt-hours. And there you can't use that. We do not have the substances or raw materials, nothing for that. So we can forget that. And in the other case, we must try to collect the energy, sun and wind in areas where we get a maximum harvest to save all those raw materials we need to produce them. And most of all, what I didn't mention, we do not have the engineers to do that. We do not have sufficient educated people to do all that. So this is a long way.
There's a question from the online audience. Would methane production on large scale not be too dangerous because of the hazard of leaking a very potent greenhouse gas?
Yes, this is an issue, definitely. But leaking is always a defect. Leaking could be, engineering-wise, kept small. It is an issue, we must take care of that. But things shouldn't happen like with Nord Stream 1 and 2, where millions of tons just escaped. This should not happen. And you have today, for instance, your gas boiler at home. It operates with a very high air excess, so that almost no methane can escape. And when you operate engines on methane, then you have an after treatment to capture methane.
Okay, I guess in the interest of time, we have to move on. Keep further questions for the reception afterwards. And thank you, Georg. The next speaker of our session is Keywan Riahi. He's director of the Energy, Climate and Environment program at the International Institute for Applied Systems Analysis, IASA, in Luxembourg. Keywan Riahi is also a member of the Commission for Climate and Air Quality, and his research is internationally highly acknowledged. Just to mention, in 2020, he was ranked as the most influential climate scientist worldwide. A year ago, in March 2022, he was also appointed to the European Scientific Advisory Board on Climate Change, which provides scientific advice to underpin climate action and efforts by the European Union to reach climate neutrality by 2050. And I mentioned this because this is highly relevant now to his talk. It goes exactly into this direction towards an energy system with net zero greenhouse gas emissions. Keywan.
Yeah. Thank you very much, Victor, for the kind introduction. It's a real pleasure to be here today and to give this this small talk. Let me perhaps oops, I hope I didn't do. Okay. Let me go back again. Okay, so let me perhaps start my talk by reminding ourselves about the fundamental role that energy plays in society. So energy fundamentally shaped our living environment. We need energy practically for all economic activities, but also for well-being. And it has been the high energy density of fossil fuels which enabled us the quality of life that we all appreciate today. But at the same time, the system has a number of important challenges, and there are complex interdependencies where the energy system increasingly has negative impacts. This has negative impacts on climate change. It's perhaps the main cause of climate change. It causes air pollution. Increasingly, we have competition for land between energy resources, for biodiversity and food. We are vulnerable to energy security issues, and we have experienced this particularly in the recent years, how vulnerability and dependency on imports for energy resources from other countries can economically affect us all. And in many places of the world, actually, we have lack of energy access. So billions of people globally, 40% of the people at the world either do not have access to reliable electricity, or they do not have access to clean cooking, which is the main mortality of the energy system. Yeah, so we need to connect those people. The mortality there is even bigger than the mortality that we expect from climate change. So big challenges for the energy system. This is definitely the right button. Großer Knopf in der Mitte, das war er. Der obere ist der, ja genau. So in order to transform our energy system, and particularly in order to reduce greenhouse gas emissions that are associated with the use of fossil energy. And in order to achieve the climate objectives, we need rapid and immediate emission reductions basically across all energy sectors. The challenge here is that we need to achieve net zero GHG emissions in order to halt climate change. So it's not enough to reduce just 50%, 70%. We really need to achieve net zero emissions in order to stop climate change. For this, we have a range of different technologies available. Some of them have been introduced today. But probably technological solutions alone will not be sufficient to achieve net zero emissions. We need to think about how to restructure our society, and we need to think about also how our lifestyles and how behavioral changes, and how we can change our provisioning systems and service systems at the demand side in order to make the right choices of the technologies at the end. And in order to achieve this, I think it is inevitable that we invest into a new system. So Georg Brasseur is absolutely right. If we want to change the system, we need to invest into new infrastructure. We cannot just continue to rely on the same infrastructure and hope that gradual or incremental changes will solve the problem. We need to invest into a new system so that we in 10, 20 years can switch to a system which has absolutely no emissions. Next slide, please. Thank you. So what does carbon neutrality mean? Carbon neutrality basically doesn't mean that each activity on this planet needs to have net zero emissions. So we will need to reduce emissions in many of the sectors. So mitigation will need to play a role. But there will be sectors which are difficult or hard to abate, where we will have residual emissions. This is particularly the industrial sector. To some extent, the transport sector, where we will need to compensate emissions from those sources by increased planetary sink or negative emissions by other activities. So we will need to achieve a balance between residual emissions, where we have reduced emissions by 90% or even more, with negative emissions that we need to create in other parts of the world and other parts of the sector, and I will come back to that. I'm not sure what I'm doing wrong here. And in order to stabilize climate consistent with the Paris Agreement, we need at the global level to achieve greenhouse gas neutrality between 2050 and 2070. And consistent with that, the EU has adopted a net zero GHG emissions by 2050 as an objective. Can I have a new one, please? But the people in the back are doing that, not me. Kurz drücken. Aha. Okay. Yeah, and how big does this, so there is basically from a systems perspective, it's important to understand how much in terms of emissions reductions and structural change we need to achieve in the system really depends on to which extent can we build up this atmospheric sink to remove CO2 from the atmosphere. The more successful we are in building up the sink, the more lenient we can be with steep structural changes in the sectors. And those things need to fit together at the end. And if you look into different studies from the literature, the sink that we will need by around 2050 globally is about 5 to 10 gigatons of CO2 that would need to be removed out of the atmosphere. That's about 10% of today's emissions. So that's what the major studies tell us how big the sink needs to be. And in Europe, the sink would be between a few hundreds of megatons of CO2 to be removed from the atmosphere so that we can achieve carbon neutrality. At the same time, this has important implications for the timing of emissions reductions and decarbonization across different sectors. It means that those sectors that in the long term should create the negative emissions and the sink, they need actually to decarbonize well before the overall system achieves net zero. Yeah, so if you want to achieve net zero in 2050 with the full system, the energy sector, which is basically a possible source of future negative emissions, need to achieve a net zero emissions already earlier. And in most of the studies, this is even 10 to 20 years earlier. So Georg was alluding to challenges how to transform the electricity system. Actually, the electricity system needs to be there first. We're talking not about 2050, we're talking about 2040, perhaps even before that, so that we can enable that transformation. And of course, also afforestation sector and the whole land sector needs to be there earlier than the demand side sectors like buildings, transport, and industry, where we will have residual emissions. Generally, if we look into the big transformations, there are two main perspectives that you find in different studies that looked into the pathways. There is more or less the conventional pathway where a lot of the change is happening to big infrastructure projects. We change supply. So basically we change our big supply systems. This means a lot of policy inertia because it takes time until we build those new infrastructure. It means also overshoot of our climate targets, relying later on that we can, to negative emissions, reduce greenhouse gases again from the atmosphere. So that's one way that we could do it. I would argue there is another way, a more rapid way to transform the system, and this is a transformation to a much more stronger focus on the demand side, focusing on granular technologies that can diffuse more quickly into the markets and also have the potential to learn more quickly. So if you look into diffusion of historical technologies, small-scale technologies diffuse faster into the markets, and small-scale technologies learn faster because you repeat the same experiment more often, and because of this more rapid repetition of the experiments, the cost of the technologies fall faster. And this is also the reason why solar PV has managed to reduce its cost 90% in the last 10 years. So factor 10 cost improvement for solar PV. It's a small scale technology that has learned very rapidly. In many parts of the world, solar is cheaper than fossil fuels today. It's as simple as it is. Solar is cheaper. And if this trend continues, it will be also cheaper in areas where it's perhaps not optimal to be installed. And this is this type of rapid technological change based on granular and distributed systems that can help us to avoid overshoot and to avoid also reliance on more controversial technologies like negative emissions technologies. Why is this demand side transition so important? It is also so important because there is enormous potential to basically reduce emissions and energy needs by better understanding where is the wasteful behavior in the system. So if you look into, you see here different steps for different sectors basically, and you see the losses in energy from extracting primary energy from the ground all the way down to the service level. And if you look at the overall system, we use actually less than 10% of the energy that we have extracted in terms of fossil fuels, or that we get, for example, from a solar PV cell. And the reason for that is that we need to convert, we need to distribute energy and bring it to the point of user. And then most of those losses happen actually in the end-use devices. And focusing on this chain of conversions and improving the efficiency of the overall system can lead to 30 to 50% in terms of reduction of energy needs at the same service level, which is absolutely critical to address in order to reduce what I would call the obesity of the current energy system. So if you want to to change the system from the demand side, I think it's really important to recognize also that we need deep structural systems, how services are provided. And in order to do so, it's not only sufficient to change technology, it's also needed to enable a social transition. And some of it is already happening. So if you look at trends on the ground and into numbers, we see changing consumer preferences on large scale. There's a big dietary change going on at the moment. We see also a generational change in terms of materialism, particularly young people are more focused on convenience of services rather than owing a certain service. So it's not important whether I have a car or not. It's important for me that I get from A to B the quickest way in the most convenient way. And if I have a system that allows that, where I don't need a car, many people nowadays are open to this switch. 20, 30 years ago, it was much, much more difficult because the car was also a status symbol, right? It was something that you wanted to achieve regardless of the mobility that it provides. We see new business models emerging that allow us to improve sharing and circularity of the economy. We see also how digitalization is shaping our world, allowing so-called ICT convergence, so convergence of different services by digitalizing them. And we see also rapid innovation in granular technologies through integrated services. Just to provide you some numbers, here, for example, exponential growth in the consumption of meat substitutes around the world. This is growth that has been going on since quite a while and expected to continue. But also other, I think, good examples are changes in driver's license of young people. So many young people don't even have a driver's license. This is an urban phenomenon at the moment. And the question is how to bring it into rural areas. So what is the new mobility system that allows you to connect basically also in the rural area without necessarily only owning a car? I mentioned this earlier, reliance on granular technologies allows to accelerate the transition, so focusing on technologies that can be used directly at the demand side, like, for example, solar PV, new appliances, will accelerate the transition compared to big infrastructure projects. And basically, this transition means that we need to introduce at the demand side a number of different disruptive end-use innovation. And what all of them have to have in common generally is that they create a system moving away from disconnected individual appliances to a new system where appliances are connected to each other and are also exchanging information. So that you create a new system that can be controlled digitally and which allows to better integrate renewables, for example, but it also allows to create new services that are better than the services that we know at the moment. For example, instead of necessarily trying to manage the load through quickly ramping up a fossil gas power plant when the demand increases, or when wind is not blowing at some part of the system, one could also control through the utility and through basically the company which is running the network could control certain appliances and ramp them down at that point in time. There are appliances that do not need to run all the time at 100%. Where you can go down to 80%. You won't even as a consumer feel it in your household. So whether your refrigerator is running at 100% or 80% for 5 minutes will not be observed by us. But it needs a new way how these individual appliances basically communicate with the grid and communicate also with a new digitally organized system. Many studies show also how this can change mobility. Basically, I want to give you an example here about Dublin. This is a study by the OECD ITF 2018. It shows more or less that with 2% of the transport infrastructure in Dublin, you can achieve the same quality of mobility service than today, through shared mobility and also to basically better organizing existing rail, but also light rail transit in Dublin. You would reduce passenger kilometers by almost 40%. You would reduce emissions just by reorganizing mobility by 30%. You would reduce congestion by 40%. Actually, that's the most annoying part of rural traffic. It is congestion. And you would get other co-benefits by it. By removing 95% of all the cars from the streets, you free up space, which is then there also for social interactions, for greening of the cities, and you create multiple co-benefits, I would argue, by increasing the quality of life generally in the city, but by allowing at the same time the same type of mobility. And that's, I think, that's what I meant earlier with connecting devices and letting devices talk to each other. In parallel, of course, of those demand-side changes, and also actually enabled to demand-side fundamental restructuring of some of the provisioning systems, would need to achieve quite rapid electrification, including increasing the share of renewable energy. It will always be a portfolio, so it will never be 100% wind takes over everything or 100% solar takes over everything. As Georg Brasseur nicely showed, this would give you quite huge numbers, and you would also not want to be energy autonomous in Europe. That's not our objective. But we want to design a system where you maximize the renewable generation within Europe and try to reduce imports quite massively in order to basically allow carbonaceous fuels to get to industries. And that's actually possible at relatively, massively scaled up renewable energy within Europe. The big question, and we heard, I think, now a really nice introduction into storage, is how would we store energy in the future? And as we heard already, it's not only about storing energy for a day or for a week, it's about storing energy over years and seasonally. And pump hydro is one option, but there are many other unconventional options as well, which we need to research and which we need to understand better. Most of these storage proposals on the table deal with basically the elevation, the potential energy for either masses or from liquids. Yeah, pumped hydro, liquid, you basically pump water up and then let it to a turbine. You can do the same with existing infrastructure, like, for example, in metropolitan areas with many skyscrapers, you can use lifts as energy storage. You can use gravity energy storage, either in coastal areas. But perhaps the most interesting ones are those where here we have the Alps, we pump up water up the hill and then let it to a turbine. If you have a coastal area with deep ocean, you could also press things underwater and have Beyonce storage power plants. Or you can do compressed air in deep ocean. So basically, instead of pumping water up the hill, one can compress air and pump it underwater, and then decompress it when you need it. Generally, energy storage cycles and storage size matters, and not all storage types are useful for every energy storage activity that we need. Batteries, as we heard also earlier, are useful generally for daily storage, but if you go to monthly or weekly or seasonally, we need to move to gravity storage, we need to move to pumped storage, and also to deep ocean storage activities. And the most powerful, of course, are those where we have liquid fuels like hydrogen or synthetic fuels combined with carbonaceous fuels or ammoniac, from which we have already heard earlier. Let me perhaps conclude with a few slides on, first of all, the big shift that needs to happen in terms of energy investments. So it's not only the case that we need already by 2030 shift 80% of all the investment from fossil investments into zero carbon investments. The need to shift this early is really important because any new investment has a long lifetime. If we continue to invest into fossil infrastructure for the transition, this will have long-term implications. We'll not manage the transition also in the long term because we don't want to strand new investments into infrastructure. This includes gas pipelines. This includes many of the infrastructures which we should run until the end of their lifetimes, but not beyond this. And if you look at the investment portfolios, here you can basically see the investment portfolio today. Here you can see the massive upscaling of renewable, or not renewable, zero carbon investment portfolio already by 2030. This whole part here is about transmission and distribution and storage. So transmission, distribution and storage investments are as big as the investment in solar and wind together here. So that's really important to see, and basically phasing out coal investments immediately. Let me conclude perhaps with the need for carbon dioxide removal. Generally, we envisage to remove CO2 from the atmosphere to forests. I think forests are an absolutely important option here, but there are in reality many other options possible as well. So there is the suggestion to use a biochar, which has the advantage that it is a granular technology. It helps to increase agricultural productivity, reduce water need, at the same time also enhance soil carbon. So we need those types of removals from the atmosphere which help us to create co-benefits in other areas as well. And there are basically carbon dioxide removal technologies on the oceans. They are technologically based, where basically you have a factory which takes CO2 out of the atmosphere, but for which you need space and energy. And then there are many nature-based solutions which probably create most of the co-benefits. Perhaps the biggest change in our thinking for achieving this transformation is to move away from the focus on individual technologies and how can I, for example, improve the efficiency of a certain technology. It's important to do, to a more systemic perspective where I look into new technologies and how they can satisfy multiple services at the same time and enhance the consumer choices and preferences. And the mobile phone is, I think, a good example how this digital integration has been achieved. The mobile phone can replace lots of different other energy-intensive services that we used to have, other appliances that we used to have at home. The issue is how to design our system that we don't use our mobile phone as the remote for these other devices, but really digitalize as many of those services as we can in one device. Thank you very much. Thank you.
Thank you very much, Keywan. I think technological development could be a two-sided sword, and you showed the mobile phone. There's a lot of computing behind that, services, artificial intelligence. They may help us to understand better and to balance off energy production and consumption, but at the same time, the technology as such consumes energy as well. I would be really interested to see your perspective on that.
Yeah, so you can have. I mean, the art will be to use digitalization in a way that it does not create a host of new services that we don't even know yet. I mean, it will happen as well. But to use digitalization to make our whole industrial metabolism more efficient and to enhance and steer choices of people towards digital solutions which allow us to decarbonize. Yeah, and this requires some steering as well. Yeah, so it would be. I can imagine many situations where we create, for example, a financial system which is based on bitcoins and create a lot of energy demand, which is absolutely unnecessary. So you need political steering of the options so that basically also digitalization goes into a direction where it is sustainable.
I think steering is indeed the key here. Yeah. Floor is open. Simone.
Thank you, Keywan. This was really a very inspirational presentation, I found, and I admire your optimism in terms of visualizing a future in which technological problems help solve, problems are solved, and also social transformation is achieved. I'm wondering, what do you consider to be the biggest obstacles? You were not talking about the obstacles that need to be overcome beyond technology. I mean, just also from your broad scope, which obstacles do you consider largest? And then a second, very different question. You made the distinction and between supply and demand side solutions, and I also work with that, and we are having discussions to which extent such distinction is useful when we talk, for example, about supply chains. And there I'm also curious to hear what your thoughts on this or what your position is. Thank you.
This is a really. So I tried also to be positive because I think the obstacles are very visible. I think the biggest question is about the sequencing of policies. So how do you introduce this change that you bring most of the society on board? Yeah, so it's thinking about the mobility transition. I think the wrongest thing that you can do is that you price alternatives right now, where people actually in many circumstances don't have the alternative. You cannot put a CO2 price on gasoline. At the same time, the only way to get from, Ebrechtsdorf to Vienna is by car. So you need to invest into this alternative system. So you need to have massive investments to enable to enable choices, and you need also to reform. You need to tackle a digital data problem. So digital data should not be something that big companies use for their profits. Data is not there to steer consumption needs. Data needs to be there with very clear hierarchy of access so that we as society can benefit from it. It doesn't mean that it should not be business. It should be business at the end, because also those data providers of the new services, they create a new business. But it needs to happen in a way that it helps us in the transformation. And it's not used for a certain profit, which is damaging. And I think this is really delicate, and it is not an easy thing. The biggest barrier here is privacy. So everybody seems to be fine to give all the information about your privacy to Facebook. But if you try to tell somebody, the net is going to control your refrigerator, I think you have a lot of convincing to do. Although the latter one is what I think should do at the end.
Thank you very much, Keywan, for this fantastic presentation. And I agree with Simone that it's really nice to hear somebody speaking for a potentially bright but very energy efficient future. There's one observation I made, and that is you are using a word which is called meat replacement, which already tells you something about the current trajectory. Yeah, I would call it protein source. because that's a completely different way of looking at the world. And why am I saying this? Because you mentioned in passing several health co-benefits. You mentioned that a lot of people die from unhealthy ways of cooking. That means they get a lot of carbon into their lungs and they die prematurely. So there is a huge health co-benefit of getting energy to these people. And there are also other health co-benefits which you did not really mention. And by now, I think that what the COVID pandemic has shown us, that if it's about people's personal health, they will endure way more restrictions and accept way more community-based action than they do for the climate crisis. There are a few recalcitrant non-vaxxers protesting, but the majority of people actually wore their masks, did not go out, because they understood they had their own benefit. So I'm continuously asking myself if talking about the health co-benefits of our interventions into the energy system would not be a way of reaching out to behavioral change being accepted more readily. I just want to hear what you think about this.
I think health is a very emotional and strong argument. So you can reach people with the health argument. At the same time, I think I'm deeply convinced that the co-benefits will not be enough. So co-benefits will be more important to make a certain option acceptable, perhaps to be perceived as better. But what people want is the service. Yeah, so you will not convince people not to travel to Graz because the co-benefit is that there are health improvements for everybody, which is without doubt the case. Yeah, so I think you can argue with the co-benefit, but what you need at the end is a better service that provides you that co-benefit in addition.
Yeah. Thank you very much. I guess we have to move on. Thank you, Keywan.
Thank you.
It's now my pleasure to invite Karl Steininger to the stage. He's Professor of Climate Economics and Sustainable Transition at the Wegener Center for Climate and Global Change at the University of Graz. Karl is also a member of the Commission for Climate and Air Quality of the Academy. His research is focused on climate and energy economics and policy, low carbon transition and transport economics, and as such comes with a solid foundation to address energy transition from the energy trade perspective, in particular over long distances. Karl, the stage is yours.
Thank you, Victor, for the introduction and also for co-leading this working group together with Wilfried. I was very thankful when this working group convened for the first time, and I really enjoy the exchange and discussion today here. I will start with the potentials and cost development of renewable electricity, move on to interhemispheric trade and introduce a small energy trade model, continue with the empirical exploration of the orders of magnitude that are involved if we trade energy, and conclude with how to trade energy, what forms. Is it direct electricity trade with transmission lines? Is it energy carriers? And what benefits and trade-offs come with that? So to place this talk in today's discussion, I fully support the energy demand reduction plea that Georg Brasseur has put forward, or the rapid transformation through demand-side solutions, service-led transformation, service efficiency that Keywan Riahi has just put forward. And I will zoom in now, once we have done all that, on the electricity system again. We still have an issue to solve there, how to supply the remaining electricity that's still there, the remaining electricity demand that's still there. And as Georg Brasseur has also put in his presentation, we do see a transformation of the energy system towards electricity. There is industry moving towards renewable produced hydrogen, steel, for example. There is the transport sector to electric vehicles, and there is the heating sector to heat pumps. So that's why electricity becomes such an important issue in a future energy system. And if we look at the physical potential, you see here on the left-hand side the renewable potentials, and these are, the renewable ones are annual. For example, the biggest one here, annual solar irradiation to the Earth. Then we have wind, biomass, geothermal, ocean, hydro. This is current global energy consumption per year. And here on the right-hand side, we have the fossil reserves, but they are in total. So they are not annual, so they are for the time being. So we see that tremendous amount of, in particular, solar, but also wind. Now looking at the cost development over the last 240 years, we see first the primary resources, oil, coal and gas, useful energy cost, pretty stable. Then we have the oil price shock and gas moving with it. Then we have two forms of electricity, by coal and by gas. You see them here. And then we have the renewables. And in the renewables, I particularly want to point out solar, PV electricity, the price came really down. Also batteries here, and power to X. And as Keywan already put forward, in many regions in the world, solar has become the cheapest source. So that's why solar is so crucial. PV modules alone since 2010, the price has declined, the costs have declined by factor 10, batteries by factor 8. And The Economist therefore put on his title page, 21st Century Power, how clean energy will remake geopolitics, because it's no longer that we are dependent on fossil source countries, but we will build up a different worldwide energy system. Now, what's the trouble with and now I focus in particular on the biggest and now cheapest source, photovoltaics. What's the trouble with it? Here we see the supply over the year in daily insolation for a northern European, Hamburg, for example, here, for also northern hemispheric, but closer to the equator, Saudi Arabia, supply over a 3-year circle here. 3-day moving average, 7-day moving average, and 50-day moving average. And what we see is that, for example, for Saudi Arabia, there is quite a difference between summer supply and winter supply. The absolute difference is very similar for a location here in Hamburg, but as a less favorable site, more cloudy areas, therefore we have overall less supply. But, as you know, the Earth has also a southern hemisphere, and luckily there is exactly opposite seasonal patterns there. And if you combine northern patterns, northern hemisphere with southern hemisphere, then you get pretty much a stable supply across the year, which would mean we would need to have some energy trade between the hemispheres. And for this interhemispheric trade, I make an experiment now. I take you to one economic model, an economic model where we have two goods, electricity that's produced in around December or around June, so in those 2.5 years, in two regions, northern and southern hemisphere, and we have two technologies, photovoltaics or some fossil or other baseload backup technology. And we think of photovoltaics now not of just the module itself, but including some storage to balance across a 50-day circle to have continuously dispatchable PV within the season. Now, the economic model I use is a trade model where first we can have the backup, the fossil technology, and produce with a given capacity some amount of electricity around December and some amount of electricity around June. And if you have it year-round, full capacity, then it's the same amount you produce in December and you produce in the period around December, which is on the northern hemisphere the winter and the southern hemisphere the summer, as it is in the other season. You could now theoretically switch some of your variable costs, some of your fuel costs in one season to still have the overall total same full total costs, but to switch it to a higher capacity to be used in only part of the year. So you could increase your production in the northern summer, for example, and only at the cost of reducing the northern winter production. So this is a so-called, what we economists call a production possibility frontier here. Now we have the choice of choosing also a second technology. We could shift from our fossil technology to photovoltaics. And that means if you're in the northern hemisphere, that you could go up to just have photovoltaics, then you would produce a lot in the northern summer in June and quite a little, quite less in the northern winter. Or you could do any point in between. That's the production possibility of shifting more and more of your fossil capacity to photovoltaic. In the southern hemisphere, it looks like that because there you have it mainly in the southern summer, which is around December. Now, if you produce there in the southern hemisphere and here in the northern hemisphere, then you could trade and you could, would there be no transmission costs, no trade costs, you could produce on any of these, you could trade to reach any of these points here, so that the benefits of trade would be for the same cost of production, you would gain quite a lot more of energy, or for the same amount of energy, it would be much cheaper. Now, if we do have transmission costs, then of course, producing in the south and transmitting it to the north would mean there is some losses. You can only have less. But still, as long, depending on the level of the transmission costs, there might still be a benefit of trading between north and south. Now, what are the orders of magnitude if we use real-world data for these benefits of trade? We did an analysis with current production costs of PV and baseload technologies and found that the unit cost of just producing either PV or producing electricity either from PV or from backup is, no, that's just the unit cost of PV here. So in the north, it's pretty high. Along the equator, there are some lower numbers, which would mean that PV coverage in this idealized abstract model would just occur around the equator, because there the seasonal structure is not there. You have PV capacity really producing and being used the whole year at the same level. And only there it would also be that electricity cost then is reduced because PV is much cheaper. If we open up to trade, we could either open up to east-west trade, and then we see that there will be unit costs declining. And in these regions where unit costs will be declining because you need less storage, you trade east-west over the daily cycle, there would be some willingness to pay for electricity from or energy from the other location mainly around the equator. If you open up to north-south trade, this area of potential benefits of willingness to pay increases further north and south. And if you open up to a global grid, then you could locate the production sites to the best locations, which is not at the equator, but a little bit outside, because at the equator it's more clouds. Then we find that the willingness to pay is as high as $90 per megawatt hour for most of the globe. This is also employed in an app. You can try your own numbers of costs for PV and baseload to try out what would be the willingness to pay. What does this tell us? First, we particularly discussed in this paper that I cited before the actual transmission line electricity exchange. Of course, there is the alternative to trade this energy via hydrogen, ammonium, e-fuels, etc., as we discussed earlier today. What are the aspects of both? If we do it in transmission lines, there is a real-time dependency. This, of course, is a security issue. Hydrogen is a storage medium and ammonium, so energy storage is possible. We don't have the security issue is much smaller. On the other hand, we have much higher transmission losses, conversion losses here. Transmission losses, even over long distances with direct current, are pretty low. There's a very high initial investment here, the lines. This can be built stepwise. It can be built up stepwise. There's no leakage of the greenhouse gas potential, and as Georg Brasseur indicated, for ammonium is short-lived anyway. There is no greenhouse gas potential. For methane, we would have to be careful. And even for hydrogen, there is an indirect greenhouse gas effect because of the OH radical reducing the takeout of methane of the atmosphere. In terms of short-term security, to discuss that a little bit more, some exemplary calculation for a complete European energy supply, we would need about 150 cables of 6.2 gigawatt each, already taking care of a 10% security buffer. And then failure of up to 20 cables would hardly affect European power supply. Worst case, some demand management to avoid peak demands. Batteries can supply in the short term, but of course it's an issue of how long this failure is, whether we can, how well we can rely on the system. There is a cost advantage relative to if we stay within the hemisphere, within the continent. The trans-hemispheric design reduces electricity cost by about 50%, by up to 50%. So it's quite substantial. It reduces both PV capacity, but also mainly storage. You could also design it in a way theoretically that you don't need any storage at all by always having somewhere. Yeah. But then, of course, we come to the security issue again. So transmission lines are fostering a convergence of economic development levels because they work best economically when you have on both ends the same demand level. If we link up to some global hemisphere country where there's less demand, it could be the trade pattern shift, and that, for example, energy intensive industry moves there, and then it's embodied energy trade of, for example, steel coming to Europe. Buckminster Fuller, when he was asked by a 12-year-old boy, how would you suggest solving international problems without violence? He answered, I always try to solve problems by some artifact, some tool or invention that makes what people are doing obsolete, so that it makes this particular kind of problem no longer relevant. My answer would be to develop a world energy grid, an electric grid where everybody is on the same grid. all of a sudden there would be no problems anymore, no international troubles. Our new economic basis wouldn't be gold or dollars, it would be kilowatt hours. So the very future-oriented perspective here. This points out the issue that geopolitics, fossil fuels are often concentrated in politically unstable regions, raising geopolitical conflict potential as we see just now in the world. Renewables much more evenly spread around the globe, rich supply can contribute to geopolitical risks, but of course it depends on whether we really move in that mood of international cooperation. Global deployment of renewable energy systems has a potential for developing economies, for international cooperation, for sustainable development. It can accelerate local economies, local energy coverage. But societal benefits, whether they really accrue in all the locations, depend whether we integrate the communities, particularly indigenous ones, in the planning and development of the system. There is lots of employment opportunities, most so for countries with low growth rates. Technically, there is issues of deployment of long-distance subsea cables, currently mainly employed on the above land lines. There is issues of real-time management of a global grid, but as we discussed earlier, these management issues is an issue to be solved. The more difficult is the political feasibility. We need international cooperation, irrespective of what kind of energy trade we have. There is a distribution of costs and benefits that we need to look into. Countries need to accept levels of energy dependence, but this issue is likely to move up higher on the political agenda given the substantial cost advantages of being aware that Europe cannot be energy autark. We need to depend on other regions. How to get there? Maybe it starts with connecting specific locations, maybe with hydrogen, ammonia first, maybe some links will later also be transmission lines. So my last slide, geographically diverse gains. PV has become lowest cost source of electricity, but diffusion is mainly hampered by its variability, seasonality, diurnal cycle, and short-term intermittency. I just focused on the seasonality here. Interhemispheric trade in electricity can address this variability. The higher in the geographic latitude, the more difficult it is to have PV coverage on your own. And the higher you are on the latitude, the higher are both transmission and trade costs, but also willingness to pay. So there could be equilibria where it is beneficial for the countries. Political challenges, concentration of PV capacity in regions with best resource. Should we really just go there or really spread it evenly? There's a trade-off between political acceptability and lower unit costs. And in our empirical evaluation, we spread this PV capacity evenly, not across the whole globe, but across half of the globe, best half of Earth locations. But even if you do that and go not only to the very best locations, you get this willingness to pay of $90 per megawatt hour. And not to forget, there is co-benefits if you have failures within local systems. Of course, such a extended network helps to minimize blackout risks. Thanks a lot for your attention and open to questions, of course.
Yeah, thank you very much, Karl. I think you have made it clear that energy transition is not something one can achieve on a regional or national scale, but it needs indeed international collaboration. The floor is open for questions. Verena.
Thank you very much, Karl. Unfortunately, you said fossil fuel sources are in politically unstable countries. I would suggest that the political instability of these countries is due to the fact that they have fossil fuels. And if you build this international grid, not only do you make yourself extremely vulnerable to terrorist attacks, because you can easily cut off access to the grid, and the other thing is, are we spreading instability? Political instability. I'm just playing the devil's advocate here. Thank you.
Thanks a lot. The benefit of renewable dependent grid relative to a fossil one is that there is much more alternatives where you could devote your focus on. So you're not that dependent on just a few countries. In that sense, it's more open, but you're fully right that once you have the infrastructure there, you make you dependent on some countries or some locations. It's basically a question of how, as humanity, we will be able to move to a collaborative to cooperative world, because there is, of course, then an incentive on both ends to really keep those lines intact. And the reason why, for example, in China, it's not yet implemented, those long lines, because those provinces in the middle, they always ask, well, what do I have from the line connecting the border provinces? So it's more an issue of really making sure that all along the line have a benefit. But yeah, a complex issue.
Christian. Yeah, I'd like to follow up on what Verena said. If we look at the distribution of population also between the north and the south hemisphere, and also the geologically available country size or space that we have, most of the people live on the northern hemisphere, very few live on the south. Most of the industry is in the north, very little industry in the south. And so if you produce a lot of energy in the south, it's a one-way for a long, long time, going just to the north. So they will exploit their position as much as they can, and we know right now many of the countries, with the exception of possibly Australia and New Zealand, who are in the southern hemisphere, don't have the most democratic or balanced political system. Even those countries that do have democracy, like South Africa, have huge amounts of problem with corruption, graft, and they can't even keep their energy supplier going properly. So I think what you presented is a hypothetical ideal case, but the reality check tells us that for a long time in the future to come, human nature, for example, trying to enrich themselves as much as they can and hold as much power as they can, will stand against it.
Thank you. I agree that if it begins to work that way, it will be countries that are in contact already in the Commonwealth, for example, or that have a common framework already where they can start to trade. I agree that clearly we do have this very imbalanced activity levels on the northern and southern hemisphere. So this might mean either that only up to the activity level of the southern hemisphere that can work, and beyond that we have other solutions, or it might mean that some of the energy-intensive industry is moving there, and then it's still an embodied energy trade. That's one-way trade, basically. But it would still be a trade benefit for both sides. Yeah.
Yeah, thank you very much. I think we move on and the last task from my side is now to ask Wilfried Winiwatzer to deliver the conclusions and some announcements at the end. Thank you very much for your attention, for the contributions from my side. And Wilfried, the floor is yours.
Thank you very much, Victor. Thanks to all of the speakers. I will not keep you forever in this and extend my conclusions for another hour or so, even if it has been extremely exciting. I think you have seen part of what we have experienced in the working group, a lot of interesting aspects on future possibilities to provide our societies with energy. There are lots of thoughts, lots of ideas, lots of useful and hopefully positive concepts that allow us to move forward here. I just want you to consider that we have in our working group and in the presentations today looked at both developments on the supply side and on the demand side. On the supply side, we have seen that there is huge progress regarding renewable supply of renewable energies, with cost levels for PV photovoltaic electricity production having gone down tremendously, so that we now can say photovoltaic is actually competitive, partly even without subsidies. Not in Austria, but generally costs have gone down so dramatically that we see the possibility of renewables to be cheaper than of fossil fuels. We still have the problem of storage and production that is intermittently, and that has to be better understood. And if we want to do storage with power to X scheme, power to converting to chemical substances, this comes with losses. But also fossil fuels come with lots of losses, and the standard car uses only 25% of the energy contained in the fuel for its movement. So this is something to be overcome, but we have also to look at the demand side. As Keywan has pointed out, demand side solutions that operate on small scales can be can develop much faster than than those large, bulky systems that we are so often confronted with when looking at, for example, electricity generation. We still have also to consider that in the ICT industry, we also have these bulky structures, thinking of the big players, the big companies that now are so strong in the ICT business. But there is a lot of options available that should should allow us to look into these issues more positively. Essential are also considerations on lifestyle emissions. What has not been shown today, but is part of the reports, is that there is a very large fraction of energy used also in our industrialized countries by a very small percentage of the population. And these lifestyle emissions that are not needed are certainly possibilities, opportunities to bring down the overall consumption to a level that more easily is to be matched with the renewables that are able to be generated. in a transformation of the energy system, we always have to consider to arrive at solutions that are close to a natural system, so that the fallback of it is not too difficult to be reached, so that we don't have to provide lots and lots of infrastructure to safeguard us against any failures. And here to rely on what the sun is providing, solar energy, and what the wind is providing on a small scale is certainly bringing advantages compared to too complex and bulky systems. Also an idea to further consider. We clearly will bring this idea of looking into ecosystem services when we work further on in activities that will end up in the Austrian assessment report, a report that actually Keywan is one of the co-chairs of that activity, that will provide an assessment of climate-related issues for the country of Austria, for the second time, in fact, and with a couple of people who are also here, I will provide information about ecosystems and health issues regarding the climate-related questions, allowing us to move forward into the future for Austria, for Europe, and globally to find solutions on the climate crisis that we are confronted with continuously. We will not be able to resolve this today, not in the next few years. But what we can do today is we can continue our discussions over, I don't know what we have to offer, a few sandwiches, some drinks downstairs where we had coffee. I hope the presenters will stay, and also you will stay and allow us to complete our discussions downstairs. Thank you very much. Thanks for the whole working group, and thanks for everybody attending online and in this room. Thanks a lot.